So now that we've talked a bit about what RSocket is, let's talk about its 4 interaction models. And we'll also talk briefly about its support for backpressure, because this is kind of cool. So there are 4 interaction models in RSocket: fire and forget, request response, request stream, and channel. Let's talk about each one of them in turn, and I'll give you some examples of each one. Fire and forget is essentially a one-way messaging model where the sender sends out the request and it expects no response and will receive no response whatsoever from the server. This is typically useful when there's no need for a response. So why is that a win? Like, here's an example. We've got a client proxy where we fire and forget a message, and we're going to get nothing back other than perhaps something that says this message left the client. That's about all we're going to get. Note that Spring Web Flux and Spring Web MVC don't really support this use case. You don't really have the option of doing one-way calls, because the way in which calls work with HTTP is typically two-way request response. Why is this a win? It saves network and computer processing time. You don't have to wait for a response to come back. You don't have to have any data traverse the network from server back to client. There's no need to process the requests that are coming back or the responses that are coming back. So you can basically make things a little leaner and meaner, as it were. However, this particular use case is primarily useful for applications that can support some amount of lossiness, things like non-critical event logging. And you could sort of think about this like mailing a letter. If you mail a letter with the postal system and you don't send it registered mail, or you don't send it with UPS or FedEx or whatnot, then it can get lost and you'll really never know it got lost. It'll just be fire and forget. Maybe something to think about given today is tax day. But the point is that this is the model that has the least amount of overhead, but also the lowest amount of quality of service and reliability. Something that's a little bit more reliable or trackable is the request response model, where each two-way request, which traverses both going and returning asynchronously, has a single response come back from the server. So the client sends a request and it gets a response back, even though that may occur asynchronously. This, of course, is a very, very common async use case. And Spring Web Flux supports this two-way use case for HTTP requests and responses asynchronously. And in fact, that's really worth noting. Even though things look like they're synchronous, even though it looks like a synchronous request response call, underneath there's really no blocking going on, and the overall transaction is asynchronous. The next model is called request stream. So each async request that was sent by the client will receive a stream of responses from the server replying to that request. This allows streaming of multiple response messages. So you might send over a single request with a mono, for example, and then you'll get back a flux of responses that can be streamed out to you. So rather than getting everything back in one fell swoop, the way it would occur if you had a list, for example, each element is streamed back in order. And of course, Spring Web Flux also supports this async use case for HTTP requests and stream-oriented responses. We've taken a look at a number of those examples in recent weeks when we've talked about Web Flux support for returning fluxes. Then the fourth and final interaction model is called channel, and it's a stream of async messages that can be sent bidirectionally between the client and the server. So for example, the client can send a request flux, which can be streamed over to the server over time, and in response, the server can send back a response flux, which can be streamed back to the client over time. And we've actually seen some examples of this in some of the stuff we've talked about with Web Flux. So Web Flux also supports this type of async use case for streaming fluxes, both to and from invocations. And in this case, the data stream from the client to server will coexist alongside the data stream from server to client. So that's a quick overview of the 4 interaction models. And I'll show you some examples later that will give you a better feel for how this stuff gets programmed. Let's talk briefly about backpressure. So we all know what backpressure is. Hopefully by now it's a way of ensuring that fast publishers don't overrun the resources of slower subscribers. And so in this particular case, if we've got a requester that is not able to keep up with a fast responder, it can exert back pressure on the responder to keep it from sending data so quickly. That's the basic idea. This is nice, especially in modern systems that are based on things like TCP, because it reduces the reliance on transport layer congestion control, which, if you know much about TCP/IP, has some rather quirky properties that help to deal with congestion in the internet, but also tend to make things a little bit slower and more erratic and more jittery or bursty. In general, having support for back pressure minimizes the need to buffer at any level, the network level, the application level, the device driver level, and so on and so forth. So it's often a win if you can use it properly. The way that back pressure works with RSocket is by using the subscriber subscription model that we talked about earlier when we were talking about how you can have various types of subscribers. In Project Reactor, when you are a subscriber, you can say, here's the amount of data that I can accept in one fell swoop before asking you for more data. And it works by having the subscriber get a subscription object in its onSubscribe callback, and then it can tell the publisher how much data it can accept at any one time, how many elements it can get before it needs to wait for the next chunk. So that's one way you can do back pressure. And we covered this earlier when we talked about Project Reactor and various back pressure models. It also supports the concept of request leases. And these are used to inform the requester how many requests it can send during a period of time and how much it can send during that period of time. So it's kind of like a lease where you can say, I want to get 100 events sent over the next 10 minutes. And then your lease is up and you have to try to reestablish your lease. And that's a way to basically do admission control so that the requesters are told they can ask the responder, and then the responder can decide if they have the capacity to respond to the requests. Underneath the hood, the Java RSocket implementation that we use with Spring uses Project Reactor and the Reactor Netty engine for the transport. And that is very carefully designed to be asynchronous and to be able to propagate these reactive streams signals throughout the network and across the different hosts in an efficient and scalable manner. So that's the end of the overview of the RSocket interaction models.